There's plenty of room at the bottom. These words were spoken by famous physicist Richard Feynman in 1959 during the legendary Feynman lectures. He was one of the founding fathers of modern physics and quantum mechanics. During the discovery of the physical laws that describe the behavior of atoms, he realized that there is no reason why humans would not be able to control and manipulate single atoms to their advantage. Feynman's saying expresses that realization by stating that at a very small scale there is much space to control. This launched the idea of what we now know as nanotechnology. Scientists like myself, called applied physicists, are just now mastering these laws for application, but thankfully we can rely on the incredible fabrication methods from the semiconductor industry that already led us to very powerful computers, smartphones, fast internet, and so on. This, however, is only the start. The subfield I work on are quantum dots. These are small spherical particles, each only consisting of a couple of thousands of atoms, and their size can be tuned at will. Changing the size changes the color of emission of these materials, making them useful as more efficient and cheap light sources than we have today. Quantum dots are already being used in existing technology, like the QLED television. The next generation of quantum dots have potential in other devices, like solar cells, detectors, and lasers. The latter is the focus of my research. Lasing operation is a lot more complicated than just light emission. It requires a material to amplify the light, in my case the quantum dots, but also a well thought of design. Generally, a laser consists of a cavity with the amplification material inside and two mirrors to keep the light trapped, with one mirror more reflective than the other. While continuously injecting light, the light bounces back and forth and gets amplified. A small fraction gets transmitted through one of the mirrors, which is the actual output of the laser. Our lasers are fabricated on a computer chip to allow for integration with other devices to open up more applications, but more on that later. Let's first take a look at how quantum dots are synthesized. They are created in a solution, and each of the quantum dots has organics attached to the surface, so they do not stick together. This is called a colloidal dispersion, or specifically colloidal quantum dots. Some of the reagents are put in a flask, and the flask gets heated. One of the necks is used to control the atmosphere in the flask. When the solution is on temperature, the other reagent is inserted, and the quantum dots start to grow. The growth is very fast, only a matter of minutes, and once the quantum dots reach the desired size, they can be taken from the flask. During the growth, the quantum dots change color from blue to red, which is one of their most important and interesting qualities. Often, a secondary synthesis step is added, where a different material is injected to grow a shell around the quantum dots, enhancing its properties and providing thermal insulation. Taking a more detailed look at one quantum dot, it can be seen that it consists of multiple parts, the core and the shell. The core size mainly influences the emission color of the quantum dot. To understand why, it is important to remember that light is a wave, which has a characteristic length that determines the color. When a quantum dot is small, the wavelength that can oscillate is smaller, so it will be shifted to the blue, and when it is large, it will go more to the red. Tuning this allows to choose an application at will. The shell can be a stack of multiple materials. Typical practice is to first provide a shell that enhances the quantum dot's optical properties, and then a shell to provide protection from high temperatures. Once the quantum dots are synthesized and its properties understood, they can be used to fabricate a laser. To do this, a computer chip is taken and some material is deposited on top. Silicon nitride is an ideal material for this, because it does not absorb the emission from the quantum dots and has only recently been optimized for fabrication. On this layer, the quantum dots can be deposited and then again a layer of silicon nitride, sandwiching in the quantum dot layer. Using advanced fabrication methods, not unlike those used to create the hardware of a computer, Some sort of design can then be crafted on this stack of layers, yielding in the end a small stripe that basically is a laser. By now shining light on this structure, lasing operation will occur from the side. And this is basically the task of my research. Understanding the properties of the quantum dots so the best material can be selected, and then use this material to create the optimal laser. Quantum dots have already shown their potential in application, but this potential is far from exhausted. The future will bring a wide array of applications in the light manipulation area to go for a brighter tomorrow. Or let's maybe say, a less bright but more efficient tomorrow. I have given the example of one subfield of science that leads to nanotechnology. There are many more, but all of them combined will allow us to optimize existing technology, create new technology, and generally allow for a massive increase in human quality of life. And then we will have truly filled the bottom.